Okay, good afternoon, everybody, and welcome to the second of these SPHERIC Global SPH seminars. Today we have the delight of having Dr. Steve Lynn from the University of Manchester give this talk. And so for those of you who may not have met Steve, but probably read all about his work in SPH. So Steve obtained his BSc in maths and physics from the University of Bath. This was followed by his PhD at Cardiff University. And then after short periods at Manchester and Manchester Metropolitan University, since 2014, he has been a lecturer and now a reader in SPH at the University of Manchester. And perhaps most relevant to today, in the past 10 years, Steve has published multiple seminal works on SPH, including particle shifting, multi-phase flows, and higher order SPH. So he's already made a lasting contribution to the field of SPH. So it's with great pleasure that I hand over now to Steve to give the second of these SPH talks.
Well, thank you very much, Ben. That's a very kind introduction. And hello, everyone. Thank you very much for joining. It's a real honor to be invited to give this talk, actually. So thanks very much for that to the SPHERIC committee. So what am I going to talk about? Well, I'm going to talk about new developments in incompressible SPH that myself and colleagues have been working on over the last, say, 3 or 4 years. And unfortunately for you, at various points, I may get slightly philosophical. And so I've given us the alternative title of Pressure, Particles, and Perspective. So I might just touch upon a few of these more perhaps philosophical topics at various points. And you'll see why in due course I've put particles in sort of speech quotes there. I should say that this is work, all of this work is done in collaboration with truly excellent colleagues in Manchester and truly excellent early career researchers. So perhaps I'll leave acknowledgements there to the end. But if we make a start then. So I thought I'd open with this image from the European Space Agency. It's a fantastic image, of course, and it sort of there were a couple of reasons for me starting with this. Number one was it's a very nice image to start off with. Number two, it reminds me to thank Daniel Price for giving a really excellent talk at the last event in this series. Of course, what I'm not thankful for is that Daniel's talks was so excellent it set the bar incredibly high, which means I've got quite a lot to live up to. So I hope I do. But it's also nice to sort of see images like this sometimes and put where we are now in perspective. You know, it sort of helps motivate the big questions in life sometimes. You know, like you know, what is the meaning of life? You know, of course we know that is to do SPH. Will there ever be a consistent and conservative SPH method? These really big global questions that everyone's asking. And of course, the other point I wanted to draw on from this image was that whereas a lot of SPH people work in astrophysics, my interests are far more earthbound, shall we say. So I'm a fluid dynamicist. I love fluid mechanics, and I love applying SPH to solve fluid mechanics problems. So broadly, my applications can be found in civil engineering, mechanical engineering, chemical engineering. So, you know, coastal and offshore engineering, geo-environmental flows. In the bottom right here, we have a fluidized bed reactor. But fundamentally, this sort of device where you've got basically mixing of multiple phases in a container, that can be found in any equipment, be it a nuclear power plant, be it a water treatment plant, be it an oil refinery. So it's quite a fundamental sort of chemical and mechanical process there. So I'm kind of interested in broad fluid mechanics problems across engineering. So I should make it clear from the start that this is very much a sort of engineering focused talk. And with that in mind, I thought I'd just give a personal viewpoint of what I've said we there, but in fact this this is perhaps a personal viewpoint. I should have said maybe but you know, I hope some other people sort of share this view. From an engineering standpoint, what do we want from SPH? We want it to be accurate, okay? And you know, the term second order accurate is used in quite a relaxed way in the SPH community, whereas we all know in practice it isn't. You know, for practical problems, for actual flow simulations, when we try and demonstrate convergence, we can't recover second order accuracy. So when I say accurate, I mean we've got to be up there competing with, you know, established grid-based codes and getting at least second order accuracy. If we can get better, we should get better, and I'll comment on that a bit later. We also want codes to be fast, okay? And by fast, I mean you get something useful for your engineering process, your design process, for example. You get something useful out from your simulation in a reasonable time frame. And for most practitioners, for most of us, that would be within a few hours or maybe overnight. You know, you could set your computer running overnight. You would come back in the morning with results to analyze and work on. Yeah. And of course, the third point is also really important, and I think where SPH has advantages over many other methods, in fact, is accessibility. How can we make the methods as accessible as possible to a range of different communities? So not just computational engineers, not just mathematicians, not just SPH practitioners, but people across the sciences and broader even, okay? And so there's a couple of points there, you know, minimal parameter tweaking. SPH is plagued by this, by having perhaps an over-reliance on too many parameters that we have to modify perhaps too frequently for different test cases. Setting up easy setup of domains and problems. SPH does this pretty well, I think. You know, we can set up complex geometries fairly easily. We can add physics, multiple physical effects fairly easily as well compared to most methods. But one thing to also bear in mind where I think we need some work, in fact, is making it low cost. And by low cost, I don't just mean sort of in computational expense, but I mean in terms of money, I suppose, and finances. So in terms of hardware acceleration, graphics processing units are great low-cost accelerators for computations. But if, for example, you're in a small, medium engineering consultancy, you've just employed a recent graduate engineer, you want them to be able to get up and running with a computational software suite within a fortnight or so. Can they do that with SPH? They can certainly do it with ANSYS. Can they do it with SPH? Can a company employ a relatively low-cost graduate to do real engineering problems with SPH? The answer is probably not. Okay, so these are things to sort of, in my mind, these are things that motivate me and things that we should be working on. Of course, great progress has been made across the community by the many people who are on this call, but there's still really a long way to go, I think. So this talk will discuss, in the context of incompressible SPH, how in the last few years myself and co-workers have tried to do just that, really. I've tried to make it accurate and make it fast, okay, with a mindset of trying to also keep it as accessible as possible, okay, along the lines that I've just mentioned. So I'll split this talk into two parts, roughly. So part one is making incompressible SPH accurate. Part two is making it fast. Okay, so I'll provide a bit of background and historical context first, just commenting on weakly compressible and incompressible models. I'll then go on to shifting, ALE and Highorder, and what we've done there recently and why I think there's real value in looking to this direction, in fact, in how we approach problems in the future. And then I'll jump in part two onto how we make incompressible SPH fast. Of course, we can do that with Highorder, but then how do we make it massively parallel? And also, how do we get it to run on GPUs? And quite excitingly, I'll also mention some very formative work that we're looking at on how SPH might look if it was to run, for example, on emerging quantum computers and quantum architectures. Okay. And I'll finish off with some future perspectives. Again, a personal viewpoint, of course. Okay, so part one then. all models are wrong, some are useful. I don't intend to be provocative with this quote, but it's a favorite quote of mine, to be quite honest with you. And I think it's something we should all keep in mind. We have our favorite equations there for governing isothermal Newtonian fluid mechanics, but they are wrong in certain instances, you know, at best incomplete in certain instances. When you get too small, when you get too big, when you add extra effects like temperature, magnetic effects, and so on. Okay, so I think we can all agree, though, that they are incredibly useful, at least for, say, the sort of problems I'll be looking at here, which are isothermal Newtonian sort of problems, for the most part. Okay. And in SPH, we've tended to solve these two equations in a variety of different ways. So there tends to be three principal ways we do this. So the classical way, of course, is weakly compressible SPH done explicitly. So every one of these approaches has its pros and its cons. So weakly compressible, of course, relies on an equation of state. And if this is known, and this is known for that particular material or that particular fluid, then if you've got the perfect numerical method with zero that solves this with zero error, this model as a model is absolutely valid and fine. Of course, SPH is not yet, shall we say, the perfect method, so we can't use the fullness of this, if you like, completely, because this equation, to get weak compressibility, is incredibly stiff. The method requires us then to have very small time steps, prohibitively small time steps, which results, in fact, in us having to choose a lower than physical speed of sound. Okay, so the method, in a sense, restricts what we can model physically by adopting a weakly compressible approach. Okay, if we go on to incompressible, this, in a sense, came slightly later from the classical weakly compressible SPH method and emerged sort of in an effort to circumvent some of the issues around pressure predictions that one used to get with the old weakly compressible SPH schemes. Because this equation of state was so stiff, high frequency, highly oscillatory pressure noise was always really quite visible in the method. And so by jumping to incompressible SPH, by assuming incompressibility and by solving pressure based on the Poisson equation, by doing that implicitly, one got far cleaner pressures, essentially due to the fact that the Laplacian acted as a smoother for the pressure. One got far cleaner pressures, and of course, because this was implicit, one could also use much larger time steps, okay, to solve their problem. Of course, this has its problems as well. I mean, you know, this is strict incompressibility done exactly is an impossibility. There's no material or substance in the universe that is strictly incompressible. Okay, but nevertheless, this is a fairly common approximation and a really useful one across fluid mechanics, you know, not just in SPH. So there's a good basis to look at this as a viable SPH method. And then, of course, an alternative is to do weak compressibility, but implicitly. And colleagues such as Kaya have developed SPH models that do just this. And there's a lot of merit, in fact, in doing this, because you kind of get around issues with both of these approaches, and the fact that you can get true compressibility with correct speeds of sound while also having the implicitness that gives you a chance for smoother pressures and larger time steps. Okay, so each of these do have pros and cons, but I'll focus on this talk on what we've done recently with developing incompressible SPH. Okay, so I just thought I'd highlight some of the examples of the pressure noise you would typically see with weakly compressible. Okay, so for example, this is from the Lee et al. Paper in 2008, and only using turbulent viscosity as a sort of anticipated mechanism, you still get very noisy pressure fields. Okay, again, without treatments such as artificial viscosity, without Shepard filtering, you get very noisy pressure fields, typically with really compressible SPH. The benefit of incompressible was you could just swap out, pardon me, you could just swap out the explicit equation of state, replace it with a Praslin equation, and for example, in this test case, get far smoother pressures from your Praslin equation than doing things explicitly. Okay, so this sort of motivated, I think, a real eagerness to sort of look into ISPH and incompressible SPH as a simulation methodology. However, that still had its issues, okay, when we started looking at incompressible SPH first of all. So you think of incompressible SPH, it requires, strictly speaking, a constant density following the particle, okay? So if you've got that, you've got no self-regulation mechanism, if you like, when particles get close together and when they clump up. And as you can see in this movie, that causes, in fact, particles to follow streamlines really quite accurately, but then clump up, and which can lead to, in fact, catastrophic instabilities in the incompressible SPH method, where it just completely blows up. Okay, so this is an example of a Taylor-Green vortex flow, where you get these very nice vortices forming, but for an incompressible constant density SPH approach, you get failure pretty quickly. So this led people to look at how we could sort of get around this, and this came to give us shifting, okay, or a particle regularization mechanism. So for those who aren't aware, shifting is basically a mechanism that knocks particles off their streamlines, and it does that based on local concentrations of particles or local densities, okay? So this displacement that knocks a particle off its streamline, that's a very small displacement, but it's done very frequently, every time step, say. And it provides a more uniform distribution. So distributions that would look like this end up looking like this, okay? And of course, the whole reason behind that was to maintain stability, but also to increase accuracy, because as we know from analysis from Quinlan et al., for example, if we try and minimize the non-uniformity parameter here, we get more accurate SPH approximations, okay? So shifting sort of started off with works by Nesta and Rui Zhu, well, over 10 years ago now. And this was the original form for shifting, for the displacement, this delta R that you would give particles to knock them off streamlines, okay? Since then, of course, the Lind et al. 2012 paper gave us a way of doing this that called upon more natural SPH functions. So, for example, called upon the kernel gradient to do the hard work, which was a bit more natural to the SPH method, I think, and allowed us to do a bit, to give it greater generality, for example, in how we'd approach free surface flows in incompressible SPH, for example. So you can see by adding a shifting mechanism of either of these sorts, you could turn a Taylor-Green flow into something that ran very stably and very accurately for quite a long time. Of course, by knocking particles off streamlines, you're changing the flow physics. And so to get around that, when the approach was first proposed, a post-shifting variable correction was suggested as a means to correct that, okay? So you've got your shifting distance there, and this comes from a Taylor series, and the shifted variable, such as velocity or pressure, for example, could be corrected like so, okay, after the particle had been shifted. This was certainly in incompressible SPH, this was an accuracy enhancement, okay, but it in fact wasn't essential. And subsequently, from speaking with colleagues in the weakly compressible side of SPH community who've used shifting for weakly compressible SPH, it's doing this post-variable correction is actually not required, okay, to get really good results. And in fact, very recently, and more recently, in fact, the way to incorporate shifting that's gaining traction is through an arbitrary Lagrangian Eulerian formulation, where in fact the shifting velocity is not done explicitly and separately every time step as previously, as for example in Lin 2012, but is incorporated into an ALE formulation and done within the momentum equation update, for example. Okay, so the effectiveness of shifting, the effectiveness of knocking of the slight displacements to particles, whether it be done explicitly like this every time step, or whether it be incorporated into an ALE formulation like so, like it's been done recently, this has had a fair bit of success, across SPH. I think it's pretty fair to say. So a number of research groups from across the world have looked at either in ALE formulation or using explicit shifting every time step, have used it to really improve simulations and really improve both incompressible SPH and weakly compressible SPH. Okay, it's been combined, for example, with existing treatments like delta SPH, for example, to help get rid of voids, for example. So, for example, the delta plus SPH approach here is essentially delta SPH plus a sort of shifting type treatment, and it can be also put in an ALE context, like Sun et al. In their recent 2019 paper. And again, it can be applied to multi-phase flows, for example, as in Mokas et al. It's really quite effective at removing these unphysical voids you tend to get in multi-phase flows when you've got such different speeds of sound and so on. Okay, so it's a pretty effective tool, I think, shifting as a means to regularize particle distributions, as a means to stabilize simulations, and as a means to increase accuracy. So I think we can kind of, or most people I think, can sort of acknowledge that as a method in SPH, we're kind of moving away from being Lagrangian. And in fact, there's an argument to be had, you know, following Daniel Price's talk last time, there's an argument to be had whether in fact, you know, conservative SPH itself is Lagrangian. You know, we actively choose, for example, a conservative pressure gradient that we know gives us an error, but that error, of course, helps maintain conservation in momentum. Okay, and we acknowledge that as being beneficial in the longer term. Okay, so while, for example, maybe a fully consistent SPH approach might be the nearest thing we could get to Lagrangian, because we know particles are following streamlines perfectly. In fact, in practice, we're not there. We're not doing that. You know, conservative SPH doesn't do that to some extent. Shifted SPH maybe goes a bit further and doesn't update in a Lagrangian way. So I suppose what this sort of led me to, or led a few of us to think was, why don't we use the whole of this spectrum? Why can't we explore how SPH behaves along the whole of this arbitrary Lagrangian spectrum, right away from Lagrangian to fully Eulerian? And that's what we did. Okay, so Peter Stansby and myself did some initial studies on this back in 2016. So I'll just comment on those briefly. But if you're fully Eulerian, that also opens up a range of different possibilities in getting increases in accuracy. Okay, so I'll carry on with the rest of in the rest of this talk subsequently. I'll mention a couple of works we've done recently on this, including work by one of our researchers, Abu Zaid Asa, who's done some excellent work on boundary conditions in this area. Okay, but of course, one of the best things about SPH is its Lagrangian nature, so we can't lose that. So I'll comment on how we've used, you know, quasi-Lagrangian incompressible SPH to solve some really hard elastic problems also. But I'll also comment on work that's looked at combining the two. Why can't we use the both? Why can't we get the best of both worlds and employ Eulerian and Lagrangian schemes together in the same simulation? And I'll also comment on work done by George Vitakas there on doing just that, okay, on how we combine incompressible SPH with fully Lagrangian incompressible SPH in an effort to use the entirety of this ALE spectrum. Okay, so let's look at the high order and fully Eulerian stuff first. So imagine if we do, out of curiosity, just go down to the very other end of the spectrum and make our particles. And so I put particles again in speech marks, and we make them Eulerian, we make them fixed. Okay, if you do that, you immediately take away error from disorder. If you're careful in how you define your kernels, and it's really quite straightforward to define high order versions of kernels that go way beyond second order in smoothing length. If you're careful in how you choose your kernels and construct them, you can get really incredibly high accuracies for incompressible SPH. So for example, for the Taylor green flow you see here, we can see examples of essentially perfect second, fourth, and sixth order convergence, going down to errors of 10 to the minus 10. Okay, relative errors for that Taylor green vortex problem. And that's using kernels just like this. There's no extra sort of treatments there at all. It is just raw incompressible SPH with a Prasman solver and a high order kernel. Okay, so this was really quite exciting in some sense. If we were willing to open our minds a bit and explore the possibility of being Eulerian as a viable way to do, at least in part, some SPH simulations, then this exceptional high accuracy gives us a real route to doing some really challenging problems really quite accurately or efficiently. Because of course, one of the benefits of being high order is that if you want to meet a certain error, for example, I don't know, 10 to the minus 4, for example, the high order kernel or high order interpolation will get there almost instantly for a certain particle spacing. So for example, for a low value of dx using a high order kernel, this was for a Taylor-Couette flow in 2D, as I recall, but the simulation could reach the desired error in 2 minutes rather than taking 4 hours for when using a standard second order kernel. So there was basically over 100 times speed up to reach a certain error when you're working with high order interpolants, which is something that could be really, really, really beneficial. So motivated by these sort of results, we thought, well, let's take this further. So in Lind and Stansby, this was focused on fairly simple 2D geometries. There weren't high order boundary conditions. So in the Taylor-Couette flow, for example, as is periodic, you can get high order convergence really quite straightforwardly. But in the absence of high order boundaries, this perfect convergence wouldn't be achieved. You still get extremely high accuracy from high order, which is in itself very beneficial, but you wouldn't get perfect convergence. So one of our researchers, Abuzaid Nassar, has done some very nice work on giving us, in fact, high order boundary conditions to use within internal flows with Eulerian SPH. So essentially employing a Taylor series along normals to the boundary. By manipulating this, you can apply Dirichlet conditions, you can apply Neumann conditions, and with high order kernels, you can recover really excellent convergence, fourth order accurate for internal flows without much issue, So this was really, really encouraging work that really boosted the accuracy of SPH for internal flows. And there was a very nice problem Abuzaid considered, actually, that was based on 3D simulations of Taylor-Couette flows and the instabilities one sees in those simulations. So for example, there's a nice study done by Mullen, an experimental study several years ago now, well, back in the 80s, that looked at the bifurcations you get in the flow of this sort. And in fact, this flow can flip between having different numbers of vortices and cells depending on aspect ratio of the cylinders and Reynolds number and so on. So this case I'm showing here, for example, tends to be around it's for around this set of parameter values, where basically the primary stable state is the 4-cell state. And you can see that as the flow starts off, as we go back to the start shortly, the simulation will bounce around in search for this primary stable state. We'll hop between 6, maybe even 8, but finally settle down to 4 cells. So this was really nice to see that with Eulerian SPH, with the high order interpolants, with the high order boundary conditions, we could get this really complex flow behavior captured quite nicely. And of course, this compared really well to finite volume CFD, okay? And for far lower resolutions with the SPH method, we were able to capture important features in these vortices. So we had to go to really quite high resolutions in the finite volume methods. So H/80, for example, in this case, to be able to capture the same thing we were getting with the higher order method. So that's sort of, this is ongoing work in Manchester, how we're sort of trying to push this Eulerian incompressible approach forward. And Abuzid is continuing to do some really nice stuff in this regard, and hopefully maybe in the upcoming SPHERIC workshop next year, we can hear a bit more about that. But that's fully Eulerian, and like I said, a key advantage of SPH is its ability to do Lagrangian flows. So we can do just that. We can get the best of both worlds if we're willing to do so. Okay, so our work with George Fotakis has done just this, separating regions of your flow into Eulerian and into Lagrangian. Okay, so again, we apply an ALE formulation. If alpha becomes 1, then we're going to be Lagrangian, fully Lagrangian. If it's 0, we become fully Eulerian. And remarkably, you can actually get away with having a pretty much discontinuous joining of the Eulerian and Lagrangian regions when you're running a simulation. Okay, there's only a very fine interface region needed where you've got maybe some variation in this alpha parameter. So just to demonstrate the gains you can get by at least having some part of your domain as being Eulerian. If you're fully Eulerian, of course, you get really quite high accuracy. If you're Lagrangian, it's not terribly it's okay, but it's not terribly accurate. By having a mix, by choosing your Eulerian domain appropriately, you can get sizable reductions in error for really quite minimal effort, in fact, and computational expense. So this is really quite a useful thing. And in fact, when it comes then to doing free surface flows, the things we love in SPH, they become achievable, but they become enhanced in accuracy, in really quite an accessible way. So this, for example, is quite a challenging test case. This is an inviscid propagating wave. Okay, so the viscosities here will be either 0 or basically the actual fluid viscosity. So 10 to the minus 3 Pascal seconds, for example. And you can see that it's a really high quality simulation that with very minimal dissipation, in fact, I can't detect any dissipation, or there was very little dissipation when we looked at it. And it's about as sort of noise free as it's possible for an SPH simulation to get, both in velocity and pressure. So this coupling of a Lagrangian SPH scheme with an Eulerian SPH scheme, it has real benefits. Okay, it has real benefits. Of course, sometimes you have to be fully Lagrangian, or at least quasi-Lagrangian, because sometimes the flows are so complex that it's difficult to assign maybe Eulerian regions in certain ways. But of course, we're still ALE in some sense. Okay, we're still not updating with the Lagrangian velocity. So some very nice recent work by one of our researchers, Jack King, has looked at using what is essentially an ALE incompressible SPH approach for highly elastic flows. Okay, so for those who may not be aware, that when you're modeling very elastic free surface flows in particular, the elasticity itself poses a huge challenge, okay, and how you model highly elastic flows in a very stable way. There's been a long-standing problem in that community called the high Weissenberg number problem. So the Weissenberg number is in effect a dimensionless parameter that controls the elasticity of the fluid, okay. So when it gets too high, and in the old days it used to be around 1. When you get a Weissenberg number of around 1, the simulation in any method would crash, okay? But thanks to shifting incorporated within an ALE formalism like this, with careful use of how we evolve the viscoelastic stress tensors, okay, we can get really quite nice results for really very high Weissenberg numbers that have not yet been achievable in, at least to my knowledge, in SPH, okay. Of course, the benefit is also then we can also apply this to really challenging free surface flows like these extrusion problems and folding problems you see here, okay. So these are just examples of different sorts of viscoelastic fluids. So fluids that have a strong elastic component as well as a strong viscous component. So there's some really nice stuff that we've been able to do, in fact, following the use of shifting. And I think combining it with an arbitrary Lagrangian Eulerian framework and keeping that in mind and keeping the whole of that spectrum in mind has allowed us to do some really, really useful things, I think, in terms of increasing accuracy with the method, okay? So that's a nice overview, I think, of what we've done in terms of making incompressible SPH more accurate in recent years. And now I'd like to sort of jump on to part 2, if you don't mind, about how we've made incompressible SPH faster. So I've mentioned already Highorder as a route to increasing computation efficiency. So I won't mention that again, but I will jump on to what we've done to make it massively parallel, okay? So this was work undertaken in collaboration with Xiaohu Gu from the Science and Technology Facilities Council in the UK. So Xiaohu did some really excellent stuff in employing a Hilbert space filling curve from the Zoltan library to essentially do quite a complex domain decomposition. Because of course, for the challenge in SPH is when you've got a flow as complex as, say, a dam break, how do you efficiently decompose your domain and load balance that, okay, to make it run effectively on potentially thousands of MPI processes, okay? So the Hilbert space filling curve allowed us to do just this, and it sort of mapped out a sequence of connected cells that gave a geometric locality that allowed really quite efficient memory access as well, okay? So this was very nice. We had the PETSI library, that's quite a well-established open source library for the Poisson solver that worked well with this. And for 100 million particles, this was benchmarked on the UK's national supercomputer with some really, I think, quite promising results. Of course, the solver takes up the most time, at least initially, but then that tails off really quite well as you go to, we're talking, well, tens of thousands of MPI processes there, okay? So that was really quite pleased with this, and this code of course has subsequently been used to feed into the Highorder simulations also. So it's a really valuable capability to have actually. But I keep thinking about one of my first slides, and not just making it fast but also making it accessible. So of course, having an MPI code that can run on massively parallel machines is of course very good, but sometimes many researchers, many small companies, for example, in industry, might not have access to these big machines. So accelerating incompressible SPH on a GPU was also a really important thing we wanted to do. And with a really excellent PhD student of ours, Alex Chow, we were able to do just this, in fact. So working with the Dios physics code, we were able to essentially modify that, which of course is already quite established for weakly compressible SPH. But we were able to modify that and extend that to incorporate a Poisson solver solved by the Vienna CL library, and again be able to do really quite nice sort of three-dimensional flows in sort of offshore engineering for, I think off the top of my head, of the order of 5 million particles for one GPU, and get really quite good speed ups over single thread CPU codes. So again, we were really quite pleased with this as a means to, I don't know, increase sort of the accessibility, like I say, of incompressible SPH and its acceleration on different hardwares. And one thing I thought I would mention also is, talking of acceleration and speeding things up, is, of course, MPI codes are well established. GPUs are also now a well-established scientific computing tool, but it's always worth looking to the future and thinking, I mean, 10, 20, even 50 years ahead, and trying to be a bit bold in how we think the SPH method will look on the timescale of decades. And sort of with that in mind, I thought, well, how will acceleration look in the future? And quantum computers, for example, they exist. They exist now, and yes, they work for, well, essentially quite constrained problems at the moment. But there is certainly a target on the UK scientific community side to have a universal quantum computer within the next 50 to 100 years. Okay, so I mean, I'm talking unbelievable timescales, of course, but it's worth thinking about now. And this got me to think about, well, how would SPH look if it was to be computed on a quantum computer? Okay, so this is quite formative work, but one of our postdocs, Tony Williams, did some nice work on this, looking at how SPH might fit on a quantum machine. Of course, quantum computers are quite different to conventional computers. Whereas conventional computers flip bits, 0 or 1 to do, operations like addition and so on. With quantum computers, you've got what's called a quantum bit or qubit, and that's, if you like, a superposition of bits, which is operated on by quantum operators, and it's that. And in that quantum superposition, a lot of operations are done all at the same time at once. Okay, and that then is the power of quantum computing, that all this can be done simultaneously, and then of course you undertake a measurement of your quantum system, and then it collapses down to give you an answer. Okay, so we just thought, well, in this qubit computational basis, how would an SPH approximation look? So, there it is. That's our nice familiar SPH approximation, and you can write that. You can actually write that in a quantum framework with appropriate quantum states A and W for the kernel, for example. Okay, so that's possible. A quantum SPH method, I believe, this is really early stage work, but the quantum SPH method is a viable thing. And you get, as you increase the number of qubits, you get very nice, quite rapid increases in accuracy, because you're able to process more and more data at the same time while the quantum computer is in this quantum superposition. You're able to do a lot more processing with more qubits. So as you increase the number of qubits, if you imagine this x-axis to be on the log scale, you can imagine this curving down even more. So this resembles or approaches what we would call exponential convergence in the error for an SPH gradient as you increase the number of qubits in your quantum computer. So this is quite nice, and it's something I think we should all be encouraged to think about going forward. In fact, how SPH will look in 10, 50, maybe even 100 years time. Okay, I mean, it sounds a bit fanciful, but I don't think there's harm in it. I don't think there's any harm in thinking about these things now. So with that in mind, we're actually really quite lucky in the SPH community, because we've got a really good leadership through the SPHERIC committee, okay? And I'm not sure many of the numerical methods have that, to be honest. Maybe they're a bit too big, perhaps, but from this SPHERIC committee, we have prioritized a set of grand challenges. And of course, if we frame our research in terms of these, then my personal viewpoints in terms of what I want from SPH, all of these follow, of course, from addressing these grand challenges. And I'd like to sort of think that for all of us doing research, I mean, these should always be at the back of our mind as we try and drive SPH forward into a method that is competitive going into the next 10, 20, 50 years, okay? So I just want to flag, in fact, a really nice review. Well, it's not really a review, it's maybe, what's the phrase? Sort of a topic paper, if you like, on grand challenges in the SPH method. So I must give hats off to Renato Van Condio for putting this together, and in fact, drawing together the expertise from a range of different academics from across the continent and putting this together. So I think it's really quite a nice paper that sets the scene for SPH and what needs to be done to make SPH a really competitive method going forward. Okay. So I think time's drawing to a close, but I thought I'd finish with some final thoughts. So I've given an overview of what we've done in Manchester in incompressible SPH over the last 3 or 4 years. I think it's become quite clear that I'm quite keen on shifting. And I'm quite keen on, in fact, embracing the fullness of this ALE spectrum. Okay, and that goes from being really quite a Lagrangian to being, in fact, fully Eulerian. And we can get the benefits of both worlds by doing that. We really can. And as a route to improved convergence, accuracy, adaptivity, and coupling, in other words, as a route to addressing, many of the grand challenges, embracing this spectrum, I think, is really something we should be thinking about. And after all, a key advantage of SPH is its flexibility. We often have debates over whether one should be conservative or consistent, and so on. In some sense, the fact we're having that debate is a good thing, because that shows how flexible the SPH method is. Okay, why not have them within one code framework, an Eulerian SPH, maybe with a conservative SPH approach? Why not have them within one simulation? If it's beneficial, if it gives you the accuracy you need to solve your problem, well, why not? And of course, one other thing to bear in mind, one other thought I've had, motivated by the quantum computing side of things, it's always beneficial, I think, to keep looking to the future, and be fanciful, I think, in many ways. Think 10, 20, 50 years ahead and how things will look. I mean, in the very near future, we will be at exascale. FPGAs, TPUs, they're already starting to be used in scientific computing. Okay, and of course, quantum is almost there as well. It's going to take a few more years, maybe a decade or so, before it becomes a bit more mainstream in our field, for example, perhaps longer. But how does SPH look now, when we're faced with all this new architecture that we're likely to see, and that will become increasingly commonplace as the decades go on? With that in mind, I think I'll draw to a close. I just want to thank, before I finish, some people. So firstly, all of the Manchester SPH group, but particularly Professor Brendan Rogers, Professor Peter Stansby, Dr. George Vatakis, Dr. Abazaid Nasser, Dr. Jack King, and Dr. Alex Chow. I'm really quite fortunate to work with really excellent colleagues and knocking heads together to discuss problems like this and come up with this work and come up with this research. That is the best part of my job, quite frankly. So thank you to the Manchester group and all those individuals, and of course thank you to the funding bodies as well, who've given us the money to do this research. because that has been also instrumental. And please check out the website. Okay, thank you.
Thank you very much, Steve.